Have you ever just stopped and thought about how incredibly fast AI has evolved, especially in understanding and generating language? It feels like one moment we had fairly simple chatbots, and then suddenly, boom, we've got AI creating really complex text, images, even video. But have you ever wondered what actually changed? What was the key thing that allowed these machines to truly get the complexity of human language of the world? Today, we're doing a deep dive into exactly that mechanism.
That's right. We're diving into Attention is All You Need. It's a landmark 2017 paper from Google, and it introduced something totally game-changing, the transformer architecture. And this paper, it isn't just like influential, it's really foundational for almost all of modern AI, a huge reason for the AI boom we're seeing right now. So our mission today is to unpack what this attention thing really means, why it was such a massive shift, and how it completely transformed AI. Not just language AI, but across many other fields too.
Okay, let's get into it. Before this big breakthrough, AI models, they really struggled with tasks that seem, well, pretty simple to us humans, like context. Think about a word like bank. In a sentence, we know instantly if it's a riverbank or a money bank, right? Just from the words around it. But older AI models, things using like bag of words or engrams, they kind of looked at each word on its own. They completely lost that vital context, couldn't really understand the nuances, especially if the related words were far apart in the text.
Yeah, and what's really interesting is how they failed. They just couldn't copy the way we humans process language.
Yeah.
We build up meaning as we go. Older models, even the ones with embeddings like Word2Vec or Glove, which did capture some meaning relationships, they were still pretty limited. They just weren't efficient at understanding these long-range dependencies, where a word's meaning might depend on something said, like 10 sentences earlier. So that raised this really big question. How can we make machines understand context the way we do?
So, okay, the old ways weren't working for these long-distance relationships in text. How did attention step in and fix this fundamental problem? Was it a totally new idea?
Well, essentially, you can think of attention as a kind of dynamic spotlight. It lets the model focus intensely on the most relevant parts of whatever input it's looking at. And crucially, it helps ignore the less important stuff, reduce the noise. So when the model is processing, say, one specific word, it can shine that spotlight back onto other words or phrases, maybe earlier in the sentence or even paragraphs before, that are most important for understanding that word's meaning right there. This ability to dynamically shift focus, that's the key. It's vital for really good language understanding and generation.
Okay, a spotlight. I like that analogy. But, my next thought is, how does a machine actually do that? What's going on under the hood? What's the mechanism?
Right, the core mechanism. It uses 3 key vectors for each token, and a token is basically a word or maybe part of a word. These are the query, the key, and the value, Q, K, and V. Think of the query, the Q, as the token you're currently focused on. It's asking a question like, what context is relevant to me? The key, K, is like a label on another token, saying this is what I'm about. And the value, V, that's the actual substance, the information content of that other token. So the model calculates attention weights, essentially scores, by comparing the query of the current token to the keys of all the other tokens, often using what's called a dot product, which is just a way to measure similarity. Then it uses these weights, these scores, to create a weighted average of all the value vectors. And there's this scaled part in scaled dot product attention. That's just a technical detail, really, to keep the numbers stable during training. But the result is it tells the model exactly how much attention to pay to each part of the input when trying to understand the current word.
Got it. QKV query asks, keys label, values provide content, and the weights decide how much of each value gets through. Now, the paper's title, Attention is All You Need, that's a pretty bold claim. It wasn't just adding attention to old models, was it? It brought in this whole new architecture, the transformer. Why was that such a huge leap, especially compared to what came before, like RNNs or LSTMs?
Yeah, connecting it to the bigger picture, the absolute revolution of the transformer was ditching sequential processing entirely. That was the radical part. RNNs, LSTMs, they were clever for their time, better at handling longer sequences, sure, but they still processed data one step at a time, word by word, essentially. This made them slow, really slow for long texts. And you couldn't easily speed them up by throwing more computing power, like GPUs, at the problem because of that sequential nature. The transformer just threw that out. It used attention as the only way to relate different parts of the sequence. And crucially, it could look at the entire sequence all at once.
Wow. Okay, so processing everything at once instead of step by step, that sounds like it would unlock some serious advantages.
Oh, absolutely. Massive advantages. And these are really why we have the AI boom today. First, parallel processing. Because it looks at the whole sequence at once, you can train these models much, much faster, like orders of magnitude faster on modern hardware. This was absolutely essential for building the giant models we see now. Second, handling long-range dependencies. It's just brilliant at connecting related ideas or words, even if they're really far apart in a document. That thing that tripped up older models, transformers nail it. Third, task flexibility. You can take the basic transformer design and adapt it pretty easily for a huge range of language tasks, translation, summarizing, answering questions, you name it. And fourth, scalability. They just scale up incredibly well. More data, bigger models. Transformers handle it efficiently, letting them learn really subtle patterns from vast amounts of text.
So these advantages, speed, handling distance, flexibility, scaling it, really sounds like a direct line to the powerful AI tools many of us are using now, like GPT or BERT.
That's exactly it. The widespread use of large language models, LLMs like GPT, BERT, Claude, you name them, it's a direct result of the transformer's ability to process huge data sets in parallel and really understand complex language patterns. It didn't just contribute to the AI boom, it arguably ignited it.
So what this means for you listening right now is that the AI smoothly writing emails, answering your questions, or even generating images from your prompts, it's standing on the shoulders of this transformer architecture. Without it, the AI landscape today would look vastly different, much slower, much less capable.
Okay, let's peel back another layer then. How are these transformer models actually put together? What are the main building blocks inside? Right, so at a high level, they have a few key stages. First, you need tokenizers. These break the raw text down into numbers, into tokens that the model can actually work with. Then there's an embedding layer. This takes those numerical tokens and also information about their position in the sequence and turns them into vectors, basically lists of numbers that represent meaning and position. These vectors then go through the core of the model, the transformer layers, stacked one after another. This is where the attention magic happens, refining the understanding layer by layer. And finally, there's usually an unembedding layer, or a prediction head, that takes the final process vectors and converts them back into something useful, like probabilities for the next word in a sequence.
You mentioned that attention spotlight earlier, but then you said the transformer uses multi-head attention. Why multiple spotlights? Is it like each head is looking for something different?
Exactly. That's a great way to put it. Having multiple heads is super powerful. Think of it like having several experts analyzing the sentence simultaneously. Maybe one attention head gets really good at spotting grammatical links, like subject-verb agreement. Another might focus purely on semantic similarity, which words mean similar things. Maybe a third looks at, how punctuation relates to clauses. So multi-head attention runs the input through several of these attention mechanisms in parallel. Each head has its own set of Q, K, and V matrices that it learns independently. They all do their spotlight thing, focusing on different aspects of the relationships in the data. Then their outputs are combined, concatenated, and processed together. This gives the model a much richer, more multifaceted understanding of the context. It really boosts performance. And these multi-head attention mechanisms, along with some other bits, are packaged into what we call transformer blocks. And these blocks are just stacked vertically, sometimes 12 layers like in the original models, but now often 96 layers or even more in the really huge models. Each layer builds on the understanding of the layer below it, getting progressively more sophisticated.
Okay, that makes sense. Multiple heads for richer understanding, stacked layers for depth. But hang on, if attention, even multi-head attention, treats the input like like a bag or set of words where order doesn't inherently matter for the mechanism itself, how does the transformer know that word order is absolutely critical in language? Dog bites man is very different from man bites dog.
Oh, yes. Excellent question. That's a crucial piece. Positional encoding. You're spot on. The core attention mechanism is permutation equivariant. Shuffle the input. And the output shuffles similarly, but the relationships it finds don't inherently depend on the original order. So to fix that, we have to explicitly give the model information about the position of each word. We add a positional embedding, or positional encoding vector, to each word's main embedding vector. This added vector tells the model where the word is in the sequence first word, second word, and so on. The original paper used a clever trick with sine and cosine waves of different frequencies. The specifics aren't super important, but the result is that it gives each position a unique signature, and importantly, allows the model to easily learn about relative positions, like how far apart two words are. It encodes the sequence order directly into the input representations. And just to round out the picture of a transformer block, besides multi-head attention and positional encoding being added at the bottom, each block usually also contains a couple other key things. There's a feed-forward network, which is just a standard neural network layer applied independently to each position. This helps process the information gleaned by the attention mechanism. And there are layer normalization steps and residual connections. Layer norm helps stabilize the training, preventing numbers from exploding or vanishing. Residual connections, or skip connections, are like bypass routes. They allow the input of a block to be added directly to its output. This helps information flow better through deep networks and makes training much easier. They're really important architectural details.
Got it. So attention, multiple heads, positional info, feed-forward nets, and these normalization and skip connection tricks all bundled into blocks and stacked deep. Now, the paper Attention is All You Need, it famously focused on machine translation to demonstrate its power. But you mentioned earlier it went way beyond that. Where else have transformers really made their mark?
Oh, the impact has been enormous, far beyond translation, but let's start there. In machine translation, the original task, transformers blew previous results out of the water. They pushed BLEU scores, that's a common metric for translation quality, from maybe the mid-20s, for older systems up to the high 30s, 40s, and beyond almost immediately. Current systems are even better.
Yeah.
A massive jump. Then, in sentiment analysis, figuring out if text is positive or negative, accuracy went from respectable, maybe around 88%, up to like 97.5% with transformer models like BERT. Huge improvement. And they quickly became the standard for things like question answering systems like what powers search engines and text summarization.
So dominant in text tasks. But it didn't stop there, did it? I feel like I hear about transformers in completely different areas now.
Absolutely not. Starting around 2020, researchers really began applying the core transformer idea beyond text across different modalities. We got vision transformers, VITs. They started treating images like sequences of patches and applying attention, achieving state-of-the-art results in image recognition, sometimes surpassing the traditional convolutional neural networks, or CNNs. And funnily enough, this success actually spurred new innovation back in CNNs too. We see them heavily used in speech recognition, in robotics, for planning and control, and of course multimodal AI. This is huge right now. Models like DALL-E, Stable Diffusion for image generation, or Sora for video generation, they often use transformers to understand the text prompt and relate it to the visual elements they create, even in really complex science. DeepMind's AlphaFold, which made incredible breakthroughs in predicting protein folding structures, uses attention mechanisms heavily. Transformers have even been used to evaluate chess positions at a superhuman level. It really makes you wonder, right? What's the next field transformers are going to revolutionize?
It's kind of mind-blowing how one core architectural idea spreads so far so fast. But these models, especially the big ones, sound incredibly complex. How on earth do people actually train them effectively? And once trained, can we get any sense of what they learned or how they're making decisions? It feels a bit like a black box.
Yeah, training them, especially the very deep ones, definitely has its challenges. They need tons of data and compute power. The original paper actually highlighted a specific trick, a learning rate warm-up. Basically, you start training with a very small learning rate, the step size the model takes when updating itself, and gradually increase it over the first phase of training. This was found to be really crucial to stop the model from just going off the rails early on. More recent techniques like pre-layer normalization, doing the normalization before the attention and feed-forward layers instead of after, have also made training more stable and sometimes faster. And a very common pattern you see everywhere is pre-train, then fine-tune. You first train a massive model on a huge general data set like scrape half the internet. This gives it broad knowledge about language and the world. Then you take that pre-trained model and fine-tune it on a smaller specific data set for the actual task you care about, like classifying medical reports or translating legal documents. This works incredibly well for transferring knowledge.
Okay, so there are tricks to get them trained. But what about understanding them? You talked about the attention spotlight. Can we actually see where that spotlight is pointing? Can we visualize the attention?
Yes, absolutely. And that's one of the really neat things about attention mechanisms. They offer a degree of interpretability that can be harder to get from other complex models. The most common way is using attention heat maps. These visualize the attention weights. You can literally see for a given word which other words in the input sequence it paid the most attention to when generating its output or understanding its context. The stronger the attention, the brighter the color on the heat map. There are also more sophisticated tools like BERT Viz, which is fantastic. It provides several ways to look inside. It has a multi-head view where you can see the attention patterns for each head separately, and you often find different heads specializing. Like one head connects pronouns to nouns, another links related verbs, and so on. It shows they learn different things. There's a model view that gives you a bigger picture, showing how these attention patterns change as information flows up through the different layers of the transformer. You can see the focus sharpening or shifting. and even a neuron view that tries to show how individual neurons contribute to those attention calculations, getting really granular. So for instance, if you train a simple transformer to just reverse a sequence of words, the attention heat maps will clearly show that when predicting the first word of the output, the model pays maximum attention to the last word of the input, and so on. A nice diagonal pattern emerges, showing it learned the reversal correctly. Or in a visual task, like finding the odd one out in a set of images using a vision transformer. The attention maps can highlight that certain heads strongly focus on comparing the features of the anomalous image against the average features of all the others. It gives us real clues about the model's reasoning process.
Wow, so we can actually peek inside and see the mechanism at work. That's fascinating. What an incredible journey, really, into the engine driving so much of modern AI. From figuring out the meaning of one ambiguous word like bank, all the way to powering these complex, creative AI systems, the attention mechanism and the transformer architecture have genuinely redefined what machines can do.
It really has. It's a perfect example of how one powerful, elegant core idea stemming from research can just ripple outwards and completely reshape a field, pushing boundaries constantly. It's why we're seeing the progress we are today.
So here's a thought to leave you with. As these attention mechanisms allow AI to focus with ever-increasing precision, looking at text, images, sound, data, across all sorts of information, how might our own human attention, our own ways of focusing and understanding the world, start to change in response?